Voyager 2 flew past Uranus once, back in 1986, and never went back. Most people assume that data has been fully understood for decades now. Case closed, nothing left to find. Then a small team of space weather scientists looked at those old numbers with fresh eyes. What they noticed had been sitting there the whole time. The spacecraft that was never supposed to reach Uranus at all. Voyager 2 launched from Cape Canaveral in August 1977, technically before its twin Voyager 1, even though Voyager 1 ended up further ahead in space thanks to a faster trajectory. The mission depended on a rare lineup of the outer planets that only happens once every 176 years, letting engineers send a single spacecraft past Jupiter, Saturn, Uranus, and Neptune, using each planet's gravity as a slingshot to the next. Miss that launch window, and nobody alive today would have seen the same opportunity come around again. NASA's original plan only guaranteed funding through the Jupiter and Saturn flybys. Extending the mission all the way out to Uranus and Neptune required years of additional approval, new software uploaded to the spacecraft from millions of miles away, and instruments that had already spent nearly a decade in the cold and radiation of deep space. Voyager 2 pulled it off anyway, and to this day, it remains the only spacecraft in history to fly past both Uranus and Neptune up close. That achievement alone would have secured its place in space history. What nobody expected was that a single measurement taken during one of those flybys would still be generating new scientific papers almost 40 years later. The flyby that confused everyone for 40 years. On January 24, 1986, Voyager 2 made its closest approach to Uranus, passing within about 81,500 kilometers of the planet's cloud tops, the only such flyby in human history. During that one pass, it discovered 11 new moons, 2 new rings, and a massive storm system nicknamed the Great Dark Spot, along with clear evidence that Uranus tilts almost completely on its side compared to every other planet in the solar system. Buried inside all that excitement was one measurement that immediately puzzled the mission's own scientists. Voyager 2's instruments detected an electron radiation belt circling Uranus that was far stronger than anyone had predicted. Comparing Uranus to other planets suggested it simply should not have been able to hold on to that much high-energy radiation, given its distance from the Sun and the relative weakness of its magnetic field compared to giants like Jupiter. Scientists filed the mystery away and moved on, since Voyager 2 was already speeding toward Neptune, and there was no way to send another spacecraft back to check. That single, unexplained reading sat quietly in mission archives for almost 4 decades, waiting for someone with better tools and a different question to look at it again. The radiation that should not have been there. Electron radiation belts form when a planet's magnetic field traps charged particles, holding them in place the way Earth's own Van Allen belts do. Every planet with a strong enough magnetic field builds up some version of this radiation, and scientists had rough models for predicting how intense those belts should be based on a planet's size, magnetic strength, and distance from the Sun. Uranus broke that model immediately. The belt Voyager 2 measured held far more energy than those calculations allowed for, and researchers had no clean explanation for where that extra energy could possibly be coming from. For years afterward, some scientists guessed that the missing energy was hiding in particles moving too fast and too energetic for Voyager's plasma instrument to properly measure. But that idea was never confirmed with real data, since no other spacecraft has ever returned to check. Uranus sat there for decades as the odd planet out, the one whose numbers simply refused to fit the pattern every other magnetized planet seemed to follow. Decades passed with the mystery technically unsolved. until researchers realized they no longer needed a new spacecraft at Uranus to make progress. They just needed decades of new data from somewhere much closer to home. The team that went back to check old data with new eyes. Researchers Robert Allen and Sarah Vines at the Southwest Research Institute decided to take a comparative approach instead of waiting for a new mission. Rather than studying Uranus in isolation, they compared Voyager 2's 1986 measurements against decades of detailed observations of Earth's own radiation belts, collected by spacecraft that did not even exist when Voyager 2 made its flyby. Allen explained their reasoning simply, saying that science has come a long way since that flyby, and that looking at Earth's radiation belt behavior gave them a fresh lens for re-examining the old Uranus numbers. Their findings, published in the journal Geophysical Research Letters, suggest the missing piece was never really missing at all. It just needed context that did not exist back in 1986, when researchers only had a handful of data points from Uranus itself and nothing to compare them against. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. That context pointed straight at a specific kind of space weather event, one nobody had seriously considered as an explanation for Uranus until Earth's own instruments caught something nearly identical happening much closer to us. The solar storm. Nobody accounted for. According to the new research, Voyager 2 likely flew past Uranus during a rare solar wind structure called a co-rotating interaction region, a kind of traveling disturbance in the flow of particles streaming out from the sun. These regions form when faster solar wind catches up to slower solar wind ahead of it, compressing the particles together into a dense, turbulent front that can sweep past the planet and disturb its entire magnetic environment. When one of these structures reaches a planet, it can generate intense, high-frequency waves capable of dramatically altering how much energy gets trapped inside that planet's radiation belts. Vines pointed to a real, well-documented example much closer to home to make the case. In 2019, Earth experienced one of these same kinds of events, and it triggered a massive acceleration of electrons inside Earth's own radiation belts, a well-measured and confirmed process thanks to modern satellites specifically built to monitor space weather. If a similar disturbance happened to be sweeping past Uranus at the exact moment Voyager 2 flew through, it would explain the unexpected surge of energy the spacecraft recorded, essentially catching the planet in the middle of its own version of a space weather storm, at exactly the wrong or right moment for a single flyby to witness. That explanation also forced scientists to rethink an old assumption about how these particular waves actually behave, one that had been sitting unchallenged since the original flyby. Why this changes what we thought we knew. For decades, the working assumption was that these high-frequency waves would scatter energetic electrons away from a planet, knocking them out of orbit and letting them fall harmlessly into the atmosphere below. Under that assumption, waves like these should have reduced Uranus's radiation levels, not boosted them, which only deepened the original mystery and left researchers searching in the wrong direction for years. More recent research on Earth's own radiation belts revealed the opposite can also happen. Under certain conditions, those same types of waves can accelerate electrons instead of scattering them, injecting even more energy into a planet's radiation belts rather than draining it away. That flip in understanding, built entirely from newer Earth-based observations, is what finally let Allen and Vines' team make sense of Voyager 2's strange old numbers. The mystery was never really about Uranus behaving in some impossible way. It was about scientists not yet knowing that this particular kind of space weather could push energy in either direction depending on the conditions. A distinction nobody could have drawn back in 1986 with the tools available at the time. Solving that one mystery did not close the book on Uranus. It reopened several others tied to the exact same flyby, some of which had barely made headlines the first time around. Other puzzles from the same flyby getting a second look. In September 2025, a separate team of researchers used new computer modeling to tackle a different Uranus riddle: the planet's apparent lack of internal heat. For decades, Uranus seemed to be the only giant planet radiating essentially no extra warmth from its interior, unlike Jupiter, Saturn, and Neptune, which all clearly generate heat from deep inside themselves. That new modeling found the opposite is likely true, showing that Uranus probably does emit more energy than it receives from the sun, just far more subtly than scientists had been looking for, hidden inside seasonal changes tied to the planet's extreme sideways tilt. Even Uranus's moon count keeps changing using old and new tools together. In August 2025, astronomers using the James Webb Space Telescope discovered a tiny new moon orbiting Uranus, only about 6 miles wide, bringing the planet's total moon count to 29. Voyager 2 never spotted this moon at all during its 1986 flyby, since the object was simply too small and too faint for instruments from that era to pick up, even flying as close as Voyager did, proving that even a close-up visit from a real spacecraft can still miss things. A powerful enough telescope can catch decades later from Earth orbit. Piece by piece, decades-old data and brand new tools are turning one 1986 flyby into an ongoing research project, and scientists studying it keep arriving at the same conclusion about what needs to happen next. Allen put it plainly after publishing the radiation belt findings, saying the results are one more reason to send a mission targeting Uranus, since similar physics could apply to systems like Neptune's as well. That recommendation lines up with an existing official priority. In 2022, a decadal survey from the National Academies of Sciences, Engineering, and Medicine, the report that helps guide NASA's major mission funding for a full decade, named a mission called the Uranus Orbiter and Probe the highest priority. Large mission for the years 2023 through 2032, beating out proposals for other worlds across the solar system. That proposed mission would send a spacecraft to orbit Uranus for several years while dropping an atmospheric probe into its clouds, directly studying the planet's magnetic field, internal heat, moons, and rings, using instruments generations more advanced than anything Voyager 2 carried in 1977. Current planning points toward a launch sometime in the early 2030s, followed by a cruise lasting well over a decade before the spacecraft would finally arrive, meaning anyone hoping to see fresh, direct data from Uranus again will likely be waiting until sometime in the mid-2040s at the earliest. While scientists plan that far future mission, the spacecraft responsible for starting this entire 40-year mystery is still out there right now, still running, still sending back a signal from a part of space nothing else built by humans has ever reached. The spacecraft that is still out there. Voyager 2 left Uranus behind in 1986 and kept going, eventually crossing into interstellar space in 2018, becoming only the second human-made object ever to leave the bubble of particles blown outward by our own sun. It survived a communication scare in the summer of 2023, when a routine command accidentally tilted its antenna away from Earth, cutting off contact for nearly 2 weeks before engineers managed to reestablish the link using a giant dish antenna in Australia, sending a high-powered signal across more than 12 billion miles just to tell the spacecraft to turn back toward home. Its power supply keeps shrinking every year with no way to fix it, since it runs on heat from decaying plutonium rather than solar panels. Engineers have already shut down most of its original 10 science instruments to stretch its working life as far as possible, using careful power-saving tricks to delay each shutdown as long as they can, with plans that could keep at least one instrument running into the 2030s. Even so, more than 35 years after it said goodbye to Uranus, the numbers it recorded during that single flyby are still producing new discoveries, still forcing scientists back to instruments and equations they thought they had already finished with. What it all adds up to nothing about this story required a brand new signal, a shocking live transmission, or a spacecraft reaching someplace nobody expected. It required patient researchers willing to pull 4-decade-old numbers back out of an archive and study them using knowledge that simply did not exist when Voyager 2 made its flyby. What they found was not a new mystery. It was the answer to an old one, hiding inside data. Humanity had been holding on to the entire time without the right lens to read it correctly. Voyager 2 is still out there right now, decades past its planned mission, and the last planet it ever visited up close is still teaching scientists something new almost 40 years later. Proof that a single flyby from the 1970s can keep rewriting itself as long as someone is willing to look again. If you enjoyed this video, make sure to subscribe, and I'll see you in the next one.